per normal, today we're going to start by looking at our topic 8 summary. So that will give us the chance to remind ourselves all about estimation, which was the first practical statistical inference technique that we've looked at. And then today will be, in terms of our new work, we'll start looking at topic 9. Still a bit too much noise in the room. Now, topic 9 is going to allow us to have a look at the other major practical technique of statistical inference, which is called hypothesis testing. Now, there is a fair bit to get through today, so we're going to have to be a little bit careful of time, but certainly let's have a look at our summary from last week. Now, estimation. In topic 7, where we reminded ourselves that statistical inference is all about using samples to draw conclusions about populations, remembering, of course, that it's the population that we ultimately want to study. It's just that we have to use a sample for practical reasons. So in topic 7, we had a look at the theory of sampling distributions to build up that understanding of how samples and populations are related, and specifically how the population distribution is linked to its corresponding sampling distribution. So for example, we could have a population distribution X, and then we might want to have a look at the sampling distribution of the sample mean X bar. And we saw that there was, in fact, a link such that if you knew what your population distribution was, you then knew what your sampling distribution would be. And in topic 7, as well as understanding that relationship, we were also able to then work out the sampling distribution and therefore answer probability questions about it. Now, last week we came along and said, well, it's fine to have some theory that tells us if this is what the population looks like, then this is what the sampling distribution looks like. But the reality is, in real life, we take a sample and we want to use that sample to say something about the population which is unknown. Now, we were able to still use our theory from topic 7, but just rearrange it a little bit, and we saw that in quite a bit of detail last week, to take that much more practical approach that formed the basis of what's known as estimation, involving point estimates and confidence intervals. So we were able to rearrange our theory and come up with some great techniques that can help us go from having one sample and therefore say our sample mean to coming up with a conclusion about our population, such as with respect to the population mean. So what I wanted to do with the summary was just initially establish some definitions for those ideas of a point estimate and confidence interval. Then we'll go through and see the formulas you use in the different cases, remembering that when we do confidence interval for means, it will depend on whether we know population standard deviation or not as to which sort of version of the formula we use. So we'll have a look at that, and of course then we'll have a look at it for proportions, both point estimates and confidence intervals. And the other thing that we did right towards the end of the lecture, we said, well, the same theory that allows us to have a confidence interval can be rearranged again such that we work out what sample size is required to achieve a particular width in our confidence interval. And in fact, we set up an error term being half the width of the confidence interval, rearranged the formulas again to come up with one for n. So I want to make sure that we've summarised that as well for both means and proportions. So a point estimate. Well, it all started with a point estimate, which we said was really just our one number best guess at a population parameter. Now, we talk about it as the value of a single statistic. So the idea is if the population parameter that we're wanting to study is population mean, we would then use our sample statistic, so that would be sample mean, as a point estimate for population mean. So the sample statistic becomes our point estimate for the population parameter. And that applies whether we're talking about means, proportions, and even later in the semester when we'll talk about standard deviation and variance. Now, you can think of it as that one number best guess, in that if you've taken one sample and, say, worked out your sample mean, maybe it comes to 50. Well, that is going to be your best guess at what the population mean is, but of course we know that the sampling process is subject to sampling error, and the reality is that that sample statistic, your sample mean, may be an underestimate of the true population mean, it may be an overestimate of the true population mean. And so a point estimate is just the one number best guess. It's not taking into account that potential for sampling error. So while a point estimate is a great starting point, we do need to expand on that idea. And we do so by literally starting with the point estimate and then adding a bit on and taking a bit off to come up with a range of numbers where we think the true population parameter lies. And that's, of course, what we call a confidence interval. So we expand on our point estimate, our one number best guess, to come up with instead a range of values where we think the true population parameter lies, such that we're taking into account that the sample statistic may be an underestimate, it may be an overestimate. So you can think of it as almost like creating a bit of a buffer for that sampling error. Now, of course, how much we add and subtract is going to have to link that to the theory, because there's still going to be some uncertainty associated with that interval. Unless my interval goes from, say, negative infinity to positive infinity, we're still not going to be 100% sure that our true population parameter is within that range, even with adding on a bit of a buffer for sampling error. So we deal with the uncertainty, of course, using probability, and that all links in back with that sampling distribution theory as well. So in the end, we have our range of values, our confidence interval, but we attach to that range of values a probability measure to say how likely it is that we think that the range does in fact contain the true population parameter. So visually, certainly think point estimate is the centre of your confidence interval. You add a bit, you subtract a bit, and that gives you that range of your interval, and you must attach to that the probability of how likely it is that the true population parameter is within that range. So whether you're talking about means or proportions, we're going to end up with a sort of standard interpretation, and that links to our long-term frequency idea from probability. So if it's a 95% confidence interval, we would talk about if we made 100 of these confidence intervals, so that involves, of course, taking a sample, making a confidence interval, taking another sample, making another sample, confidence interval. If you did that 100 times and they were all 95% confidence intervals, what you're really saying is that you'd expect 95 of those 100 intervals to actually contain the true population parameter, whereas you'd expect 5 not to. Now, when you go through this process just once in real life, obviously your one confidence interval is either right or wrong, but you know the odds of how likely it is to be correct. And of course the idea is that having that information, that measure of uncertainty, you can then think about how you use that conclusion, what kind of decisions it gets incorporated into, and certainly, as an example, if you weren't happy with only a 95% level of accuracy for that interval, well then you would look to, say, changing to a 99% confidence interval. So it's all about having the information so that you can then make well-informed decisions. Remembering that unless we have the entire population data set, we will never be 100% confident about any of our results. When you take a sample, you have sampling error, and so the uncertainty just needs to be measured so it can be factored into how we use those conclusions and decisions. So please don't forget about that interpretation and how it links into just our general understanding of probability and what that tells us. So having that knowledge, we can now think about, well, how do we implement this for means, for studying central tendency, which typically means studying the mean. Now, the point estimate for our population mean mu, remember that's what we're ultimately trying to say something about our population. So if we're talking about mean, it's population mean mu. That's why the notation is so important in the second half of the course. We would just use our sample mean as the point estimate. So the sample statistic is the point estimate for the corresponding population parameter. That's our starting point. To do a confidence interval, we need to add and subtract a bit from the point estimate. What we add and subtract will be based on a critical value times the standard error. Now, what you've got to think about when looking at the mean is that we're trying to say something about population mean. It may be that we have a case where our population standard deviation sigma is known. If that's the case, it really is just a rearrangement of that topic 7 theory that we looked at. Start with your point estimate, add and subtract a Z value based on how confident you want to be, so that's where that Z value comes from, times the standard error of your sampling distribution. And of course, to get the Z value, use your inverse table, although when it is a Z confidence interval, we have those sort of lookup values that we can just keep as a separate list for the common levels of confidence. So 90, 95, 99, you can have those Z values just written down separately on your notes page if you wanted to, or you can just always go to the table. Now, if, however, sigma is unknown, so if you don't know about your population standard deviation, we have to make an adjustment to our original confidence interval formula. Now, that adjustment includes using sample standard deviation S instead of population standard deviation. Now, that makes sense because, remember, sample standard deviation S is our point estimate for sigma. Now, having that additional point estimate using S instead of sigma does introduce a little bit more uncertainty into that calculation, and so that is modelled by also switching from a Z distribution to a T distribution. Now remember, the T distribution looks a little bit like the normal distribution, in fact a lot like the normal distribution, but it has those fatter tails. Of course, the T distribution involves degrees of freedom, and so sort of fatness of the tails will depend on that degrees of freedom parameter. It's linked to sample size, so it's sample size -1. The idea being the bigger your sample, the higher the degrees of freedom, the more accurate your results, the bigger the sample, the closer you are to your population. And so in fact, degrees of freedom when it's high, the T distribution tends back towards the normal distribution, because we don't have as much uncertainty. So a few adjustments to make, and that also is telling us that it's very important when you're doing a question involving means to think carefully about whether the problem gives you information about sigma, whether it's known or unknown. It's the same in real life. You have to really think about whether you have that information or not, so that you then use the appropriate formula. Now, in terms of the T critical value, well again, it comes from tables. Now, because we've got that degrees of freedom parameter, pretty much you've just got to use your T tables. You look up the row based on the degrees of freedom, and then you can look up the upper tail area in the particular column, and that will give you your T cutoff. So if you haven't already, please make sure you go into Blackboard and download those final exam tables. They include the normal and the inverse normal that we had from the mid. They also include the T, as well as some other distributions that we're going to be using in the next few weeks. Okay, Now, the only other quick reminder, as per my diagram on this summary page, is that please don't forget that in rearranging that topic 7 theory to come up with the formulas for confidence intervals, we base that sort of 95% confidence as being positioned in the middle of our distribution. So what's left over, in this case 5%, gets split between those two tails. So if 95% represents 1 minus alpha, alpha is 5%, but when you're doing confidence intervals, that alpha of 5% gets split between the two tails. So we'd have alpha over 2 in each of those tails, in this case 2.5%. Now, in terms of your answer format, well, you need to be able to write it down with reference to population mean. You're coming up with an interval for population mean mu. You're using your sample mean, x bar, to come up with the confidence interval boundaries, but your conclusion, and therefore your answer, is in terms of population mean. And don't forget to clarify what level of confidence goes with it, whether it's 90, 95 or 99%. Now, in terms of rearranging those confidence interval formulas to be able to solve for n, such that if we want to specify how wide the confidence interval is going to be, and we can do that in terms of specifying e, which is the bit we add and subtract, and therefore represents half the width. If we know how big we want the interval to be, we know the level of confidence and therefore know z, and we know our population standard deviation, we can in fact solve for n and work out how big our sample size should be to achieve that particular width. Keeping in mind, of course, that the wider our confidence interval becomes, possibly the less useful it's going to be to us. So we want it to be as confined as possible. Making a bigger sample size will have the effect of reducing that confidence interval width for everything else remaining constant. But of course, increasing your sample size comes at a cost. So this rearrangement of the formula just allows you to work out, well, how big should my sample size be to achieve a particular width in the confidence interval? So you can be quite accurate and therefore not waste resources in taking, say, a sample that's even bigger than what you really needed. Now, just in terms of that formula and implementing it, it does require a figure for sigma, our population standard deviation. So if you don't have some information, past results, a pilot study, one of the ways you can estimate it is to look at the range and divide that by 6, and that's a pretty good approximation. The only other thing is, of course, when you do the calculation, if your number comes out at something like 121.2, you can't have 0.2 of a sample item, and so you must always round up, because this formula will give you the minimum n to get a certain width, and so if you round down, you would be making your interval wider rather than reducing it. So you must always round up. Even if your answer ended up as something 0.001, you still round up to the next whole number. So just a few practical things to keep in mind. But in terms of the actual computations that you need to perform, these are not too bad. I think that they're fairly straightforward once you know what formula you're using. Now, we also had a look at proportions. Remembering that, again, we're trying to say something about the population. So in this case, we're trying to say something about population proportion pi. Our point estimate would just be our sample proportion p. So point estimate, once again, sample statistic is the point estimate for our population parameter. Now, same type of formula for a confidence interval for proportion, same structure in that it's a point estimate plus minus a critical value times the standard error. We just customised it for this particular application. So our point estimate P, our sample proportion, to that we add and subtract a Z critical value, because remember our sampling distribution is normal, times our standard error. And of course our standard error, we use P as an estimate for pi, because we're trying to say something about pi. So we use our sample proportion because we don't know what pi is yet. And once again, standard error includes that sample size figure. So your final answer for the confidence interval of proportions will be in terms of population proportion pi. And again, we can rearrange our confidence interval formula whereby we set the bit that we're adding and subtracting to equal E. We rearrange and we end up with a sample size formula so that we can work out N to get a particular width in our confidence interval. That formula involves Z, pi and E being half the width, the bit that we add and subtract. So you'd have your value for Z based on how confident you were going to do your analysis at. Your E comes from how wide you want the interval to be, E just being half the width. And then pi, well, if you have some past data, you could use that. Maybe you've done a pilot study. If you have no idea what value might be for pi, well then your default would be 0.5. That will in fact maximise that equation and give you the biggest N that you could possibly need regardless of the value for pi. So if the pi happened to really be 0.3, it wouldn't matter. This formula would have still given you a sample size that's appropriate. Whether pi was really 0.99, it doesn't matter. 0.5 as a default value will give you the maximum N that you could need. So a few practical things, again, round up when you do a sample size for proportions. Bit of theory, therefore, in topic 8. It is important to have that understanding that this really all just comes from our look at sampling distributions in topic 7. Once you're comfortable with those ideas of what we're trying to achieve, what this is going to do for us, how it's taking into account things like sampling error, and that it does just come from that theory that we established in topic 7, it's really then just a matter of practice, focusing on the practical aspects. And so that involves being able to find point estimates, confidence intervals, and sample sizes. Keeping in mind that if you happen to be doing a confidence interval for means, you must be very careful as to whether you know sigma, because if you do know it, you'll use the Z version of the formula, but if you don't know sigma, you'll use the T version. But that pretty much covers topic 8.